Hello, everyone. Okay, so it's me again. If you all have been coming for this seminar, yes, I'm the host for today. So this is the second session of Why Should I Care seminar. Okay, so the first session we actually, just a brief introduction in case you don't know what is this whole seminar about. Okay, it's actually because sometimes last year there are a batch of students, there's a few students who felt very lost about what they actually study. So they decided that they should come up with a seminar and invite our professionals from outside to come here to have this seminar, to have a talk, to reassure students that what they are learning are actually applicable to the outside world. So now today we have here Professor Avi from MAE who will come and talk to us about limits, right? Okay. So So today we are all gathered here to reaffirm ourselves, to know that what we are learning every day is actually useful in your near future, whereby you all will go out and work and everything. So topic for today, like I said, is limits. So anyway, just in case you all still didn't know, we actually have a Facebook page up on Facebook, yes, and it's called Why Should I Care, correct? Why Should I Care seminar. Okay, so it would be good that you all go and search for it after that and do some sharing to boost this our crowd so that we can have more sharing with one another and share this message across to all the students around. So in everyday life, limits, there's speed limits, there's whatever limits that you all have, okay? So limits is in our everyday life. So just a simple analogy of limits, okay? Imagine you're a farmer, then you have 2 cows, okay? At every month, your cow will give birth to 2 babies. So in the long run, you have to calculate how many cows you actually have. You can actually make use of limits. Well, okay, maybe it's not a good analogy, but yeah, that's the analogy I find and how I perceive limits. So that's why I need to come for the seminar to know more. So yes, maybe you should start. Okay, sorry, my bad. Yes, my bad as a host, but yes, maybe you should start.
But this is a very good example
You can elaborate further.
about our ability to perceive limits, which is very limited. Yeah, how do you put it, Daniel? Please, my assistant, Daniel. Hello? Yeah, very nice. Is it okay? Okay, good. So first of all, let me tell you what was my feeling when Daniel asked me to present a talk about limits to mathematical students. First of all, I felt very privileged, and yet I'm feeling very privileged to be in front of you and to deliver this talk, because I think that mathematical students have the ability to pursue the truth. And I always thought that, I'm coming from an engineering science. However, well, I think that I regard myself as a mathematician. It took me a long time to realize it, though. And I always thought that the mathematical student and mathematician can be an engineer, but not other way around. It's very much related to people who are artists and people who are doing crafts. Yeah, so I regard engineering people as doing crafts, although you will find people, I hope that you are not offended by what I'm saying. He is from civil engineering. Okay? Yeah. So you will be able to find scientists and mathematicians and physicians in engineering sciences, but not all of them are such. And people who are going to study mathematics and physics from the first place, well, this makes a difference because they are pursuing something. There is something more. It's not only about making money in the real world and what are the applications of what I'm doing and what are the consequences and all this stuff. Very abstract level, okay? However, I know that people who are doing abstract stuff sometimes loses the connection to the real world. And this is basically the main purpose of this seminar series by Daniel. The first time that I realized it was back in the Technion in Israel. I have taken a course, taken much of mathematics courses during my PhD. And I've taken a course in matrix analysis, and then I realized how vast and deep this field is. However, at a certain point during the course, during the end of the course, the lecturer gave an example for what matrices are used to, are good for. And I was amazed. He gave an example from control theory. I'll not tell you much about it. I assume that you are very familiar with that, the one from civil engineering. And their matrices basically are indicative of stability in systems. And it was a very interesting example about owls and snakes and mice, something like that. It's like controlling processes in which the eigenvalues of the matrix is used to explain and to guarantee the stability of this ecosystem. So this was the first time that I realized that mathematics students, although they are dealing with very abstract notions, they are not really aware of the context in the real world. And I will try to cover just a bit about limits and to show you a few examples. Obviously, they are all related to the theme of my research. And I hope it will be very joyful for you. Let's begin. I will begin with the notion of limit as you might know it. Apparently, limits are all around us, and there is a reason for that, because we are living in a confined space. Yeah, we are very strict to a universal law of physics. So limits basically gives us they are very indicative of what we can do and what we cannot. And I would tell that, well, I'm not really exaggerating by saying that most of the things that we can do in engineering and in everyday life has to do with approximations, and this has to do with limits. So limits are very, very helpful and vital. And I wanted also to mention that in some mathematical fields, there are some limits in which people find that this is some indication of divine creativity of God, yeah, the existence of God. So in mathematics, in basic calculus, we use them to define continuity, for example. So the best way to understand that is to take a magnifying glass and to look on a curve. It might be a function or whatever that is. And then you get to see the points. Yeah. Now, if there is a continuity here, then we should expect that this infinitesimal interval, dx, as we designate it, should approach 0. This is a limit that defines continuity. Obviously, it has to do with the notion of differentiation, derivative. Okay, it's very much the same, but instead of looking at the infinitesimal distance, we look at the fractional over here, and this is known as the derivative. Okay, eventually it will give you the tangent to the line at point, or if you are working with manifolds or differential geometry or whatever, it will give you the tangent space. This is very useful because we can approximate nonlinearities. Yeah, we call this line nonlinear because it's basically nonlinear. Yeah, so we can approximate it at a point via a linear approximation, a line. And in engineering, we use that quite a lot. The other interesting application is what is known as measure theory and integration. So I assume all of you know what is an integral, but it has to do with a very vast field in mathematics known as measure theory. Will not tell you much about it, but the basic idea, everyone knows that an integral is the curve, is the area under the curve. And analogously to what you have seen in the previous slide, here we take an infinitesimal stripe in the curve. And this will give you an infinitesimal region. And then we take the sum. By taking the limit of this infinitesimal region to 0, we get an integral. Okay, I'm not going to talk whether this limit really exists. There is a point in that. Yeah? There is a point to ask whether this limit really exists. This is one of the studies in this mathematical field. What is a measure? So measure, basically, roughly, it is like when you have a curve which is non-negative. The basic idea is that this can represent like a weight. Yeah, it measures some quantity. And then what you have, basically, you can talk about infinitesimal measure. Yeah, there are some mild conditions on measure that it's supposed to fulfill. But otherwise, it's very simple. The idea is very simple. And one of the examples that I can give you is like if you want to calculate the mass of a body or something, I don't know what. And this is basically a measure. If you take the mass per unit volume, this can be regarded as a measure because it cannot be negative. Yeah. So by taking the integration, you integrate over the whole volume, you will get the mass of the body. Yeah, and one of the examples that I have given here, it's very ambitious. Yeah, you may want to compute the overall mass of the dark matter in the universe. Well, all you need to do is that someone will give you the density function here, which is denoted by F. Yeah, and I think that people are doing that today. Aren't they? Might be. Yeah, well, this is more closely related to what I'm doing, chance, luck, and order. And what I'm going to talk about, some limits in statistics and probability. And this is very fundamental. I will begin. Oh, there is an echo. Is it okay? I will begin with an anecdote. Thank you. So, for example, coin tossing. I don't know if you are taking a course in probability, but this is one of the most common examples that people are dealing with, the coin tossing example. So in everyday life, you may say 50-50 chance, 40-60 chance. So what is the exact meaning of saying so? So, for example, if you have a fair coin, yeah, you have a 50-50 chance it will fall on heads or tails. So you flip the coin, let's say 10 times, and you measure how much times you get heads and tails, and then you find out that it's not 50-50. You will take 100. Once again, it will not be 50-50. The chance that it will be 50-50 is very low. You will take 1,000. Whatever number you have, even number, obviously, it will not give you 50-50, and I can assure you that as you increase this number, the chance or the probability of getting 50-50 reduces and approaches 0. You will not have 50-50 exactly. Yeah, so what is the exact meaning of 50-50? Well, this is basically one of the interpretations of probability, and it has to do with a limit. And it says basically this very simple formula that you see here is basically the definition of a probability, one of the definitions. And it says that in order to get a probability of an event, you need to do infinitely many experiments and count the number of the outcomes of this event, the event really occurred. And obviously, in order to get a non-zero probability, you will need infinitely many outcomes, as evinced by this formula, yeah? Yeah, this is basically the probability of having tails. So you count the number of tails you get in these experiments and divide it by n, the number of total experiments. And you should take the limit of n to infinity. Well, in everyday life, obviously, we cannot approach infinity. And in engineering and in every other science, possibly, when we say infinitely many, that means practically it is a very large number. So, well, basically, it turns out that this definition of probability is a special case of a more general formulae known as the strong law of large numbers. And it says that if you take the average of random effects, you have many experiments, each of which is a random effect. You can consider it as a random effect. You take the average, then it will give you a consistent estimate, a consistent measure. And this is what we call 50-50. Yeah, when you say 50-50, you mean this is in the limit. In the limit, it will approach 50-50. Okay? Let's move on. For example, what is it good for? So there are many systems in nature, well, basically all of them, are composed of very small particles or individuals or entities. For example, this school of fish, they are swimming. Yeah, but they have a tendency to swim in a certain direction, for example. There is an order in this system. However, if you look at a specific fish, you will find out that there is random fluctuations. Why it is random? Because we cannot really tell what is going on in the brain of the fish, what he is thinking, and what causes him to steer and to swim in that manner. However, it doesn't really important for us, because if we want to express the flow of fish, we can take the strong law of large numbers. We can average the trajectories that you see here of each and every fish, and we will get the average trajectory, which basically is indicative of the flow. Yeah, so this is very much related to the law of large numbers. Yeah, that's right. But you really don't have any, you are not really intervening in the system. You cannot interfere. You see what I mean? So you get what you get. Another example of that, for example, is when you look at ants. When you have, if you ever looked at ants, they are going from the nest to find food. However, over time, there are all kinds of ants wandering around, but if you look over time, there will be a line of ants, a straight line or smooth line. If you go just a bit further from that, you will see it as a smooth line. This is about the same. What happens in nature is because the interaction between the particles, when I say particles, I mean individuals in the system, what happens is that the noise is like filtered out. This is what happens when you take average. When you take average, you basically exclude the fluctuations. This is what happens over time. So it's about the same thing. There is a guy from the Technion who proved mathematically why ants are moving in straight lines like we see. Yeah, by taking the interactions between them. A very interesting property of that is very much related. It's known as the central limit theorem. And it says something very, very simple. If you take this average and check the distribution, I don't know if you really, do they know about distributions? You know what is distribution? Well, yeah, it's very much related to probability, and basically it shows you the scattering. Yeah, for example, if you say this, I don't know, this mouse can be here with some probability, and it can be here with some probability. So this is a distribution. And if you look at the distribution of the average that I just mentioned to you, then you will find out that this is like Gaussian. normally distributed. I will show you Gaussian in a few seconds. And this is very interesting because it does not matter what is the distribution of the movement of the fish or any other individual. Eventually, you will end up with a Gaussian distribution, no matter what are the fish doing and what are the other particles doing in the system. And obviously, this is taken as a limit. When we state mathematically this statement, we take it as a limit, meaning that you need infinitely many particles, infinitely many individuals in the system. However, it turns out to be that it works quite fine if you take a large number. Yeah, for example, when people are grading you here in the university in courses, they really want to see Gaussians. They really want to see normal distributions. Yeah, so you have 100 students, and you will see like something approaching a Gaussian. However, if you have 1,000, it will be more likely that it will be Gaussian. Although I have some concerns about it, but it's really related to this talk. Yeah, so the main implication of that is that out of chaos and disorder, we can expect that on the macroscopic level of every system, of every natural phenomena in nature, we can expect to see order. And this is what we see in everyday life. Now, what you see is basically, once again, this plot you've seen before. And you have the average movement of the fish school. And then this is a Gaussian, which shows you basically how this trajectory can move. And this represents a probability. So the maximum probability will be that it will be in the middle of the Gaussian. However, there is some chance that it will be over here. But I can tell you that over time, this Gaussian shrinks. Meaning that over time, what will happen over time, and when you increase the number of fish in this school, what will happen, you will have greater certainty that it will be in the middle, because this Gaussian will be very slim, like that. Okay? What you see over here is how what is the limit here. Yeah? So you see that we take the limit with respect to the number of fish. Okay, so each and every fish can have some movement pattern which is not really important to us, because when we have a large school of fish, then it will eventually end up with the Gaussian distribution. Just another example. Well, yeah, it was, I think, in the 18th century in France that people were very much concerned about gambling. And they were seeking a betting system that is bulletproof, meaning that they should win. They should win in a couple of coin tossings or whatever that is. Yeah, and well, I'm going to talk about a system for two outcomes games, meaning that you have either, in the case of coin tossing, you will have either head or tail, or in roulette games, you will have the black-red settings. And the idea behind it's called a Martingale, yeah, and it's a betting system. And the idea is very, very simple. You basically, yeah, I will explain you the game first. Well, you, for example, flip a coin, and then if it comes heads, you will win your stake. If not, you will lose. So people ask, what should be the amount of this stake when you put it initially? So the betting system, the seemingly bulletproof betting system, is known as Martingale. It says the following thing: after you lose twice, double your stake. And the idea is that when you first win after you're lost, you will be able to recover all your previous losses, plus there is a profit which is equal to the initial stake. And it was believed that this system is really bulletproof, meaning that if you have a person with unlimited wealth, he will be able to win eventually, because the probability of heads showing is non-zero. However, nowadays, well, you don't really need to understand the mathematics about it, but nowadays martingales are very much understandable. And I think that there were many people, many gifted mathematicians working in the field of probability like Kolmogorov and the father of information theory, Shannon, who worked quite a lot with this kind of processes. It's known as stochastic processes. And there is a story that these people were gamblers, basically, wanted to win. And it can be shown, basically, that the other way around is the statement that I've just shown you can be disputed by taking the mathematical limit. And on the average, the gambler cannot really win this game. And this is shown as a limit. You ask why? Because the martingale, there is, first of all, it's a convergent process, meaning that eventually it stabilizes. And in that case, it stabilizes around 0, meaning that there is no win-win situation. You will always lose. The basic idea is that you see the Q here. What you see here, basically, Q, is the probability of winning. Okay, so when you have a fair coin, the probability of winning, what we call winning, might be equal or less than enough. And this is what you had in the casinos and where they used to play. And for that reason, they lost. If you will take this Q to be, if the probability is higher than that, then what you will have is a divergent process, meaning that eventually you will win. But this wasn't the case. And even more than that, you can use the law of large numbers in order to show that you basically, what I just told you was about on average, meaning that there is some chance, there is a probability that you will win. It might be very low, but there is a chance. However, you can show that for such processes, the probability of winning approaches 0. You will always lose. Meaning if you're an addicted gambler and you continue to bet only for the fun of it, because you have an unlimited wealth, you will lose your profit, your fortune, eventually, in the limit. This is another aspect of my work. It's about complex system evolution and knowledge discovery. I will explain just a bit. I've mentioned to you particle systems in which we have interactions in the microscopic level that give rise to what we call an emergent behavior on the macroscopic level. Every system in nature is like that. And I will give you an example. For example, this flock of birds. And we can simulate it by performing very simple 3 local rules. When I say local, I mean that every bird should follow a very simple rules known as cohesion, alignment, and separation. Yeah, and this basically forms very small groups within the system, and eventually you will have a very large flock, as you see on the right here. Obviously, it's related to swarms, schools, herds, population of people, the internet, everything basically. Statistical mechanics, quantum theory. Yeah. Okay, how limits gets into that? Well, I need to explain you this figure. And it turns out that in order for such system to self-organize, meaning to evolve and to adapt to their environment, and this is basically how human beings came into being, yeah, and every other creature came into being like that. They need to approach 2 extreme behaviors. One of them is exploitation, the other is exploration. And this is basically what you see in this figure. On the left, you can see exploitation. On the right, you can see the configuration of exploration. These are 2 limits. The limit of exploitation and the limit of exploration. Now, the abscissa, this axis that you see, it quantifies the diversity in the system. What is diversity? Diversity basically, it's roughly composed of two components. The first one is heterogeneity, meaning what is the difference between the entities, the individuals in the system. The other component is the interconnections between them, the influence between them. So in the limit of exploitation, we have a very unique configuration in which you see all the individuals are the same. I will tell you more than that, in this limit, they are all the same individual, same copy of the same, it's copies of the same individual. And this is one of the limits. The other limit on the other end is what we call the exploration. This is purely random. It appears as a purely random behavior in the system. Why it's called exploitation? Because what happens is that when you have a system, for example, a swarm of ants that looking for food sources, So what happens when they find the food source? They all came closely to this food source, and this is like they're exploiting the resources. Now, if you would put another food source, let's say 1 meter far from this specific food source, it will take some time for the system to find, I call this a system for the ants. It will take them some time to find the next food source. And this will happen only because there are some small ants wandering around doing exploration. If you haven't had these individuals that making the exploration, you will not be able to find the next stage which is represented here as a food source. And for that reason, exploration is basically taking place, and it appears to us as a random behavior, because the ant says it might have very simple rules to seek for the food source. It's about the same thing in knowledge discovery. If you look at the history of science and the history of humankind, you will see that only a few individuals out of many scientists and many engineers and many other people, only a few individuals found out breakthroughs. Okay? It was very eminent in the previous century, in which you are learning physics, you know much about it. So there are two extreme behaviors, and this is what you see over here. The figure itself, which appears like a Gaussian, well, I'm not really going to explain much about it, but it represents the connectivity or the influence in the system between the individuals. It represents it also here when you see this kind of field ball. That means that this is the same individual. Okay, so we are going in one limit into having the same individual, calling that dictatorship. And over time, what happens here is that you have many individuals, all of them are different. However, they are very much influencing each other, as you can see from the connectivity pattern. And in this limit, in this extreme limit, you can see individuals which are not really influencing one another. And this gives rise to, similarly, a random behavior. Okay. After explaining that, it was a bit tedious explaining this figure. I know. It always happens to me with this one. Let me just mention a few details about the limits. So as I mentioned to you, system, in order for them to evolve, to adapt, they need to exploit both of these limits. There is an interplay between these limits. However, in the real world, if we will try to inspect them, try to examine these limits and to find out what are they, exactly, we will not be able. For this reason, I call them transcendental or philosophical limits. They are not really approachable. They are not really reachable. They are unreachable. One of them, when we talk about pure exploitation, something which should appear as random behavior, pure exploration, this is like the diversity, I call it diversity indexes go, it approaches the limit of 1, then I call it free will, okay? So you will have to find out a system in which you can determine that this is a free will. Yeah, it's very difficult to do so because we don't have the something absolute in order to compare. What is free will? Yeah, in each and every one of you, if you look inside, you will see all kind of constraints and restrictions. And this is about the same thing in nature. And the other limit is what I have called determinism. Yeah, this is like having the same individual. Yeah, it's like cloning or something. Maybe in quantum mechanics you can do that. But then again, this is a very in the quantum level. If you take that, the two limits, and take the figure that you have seen before, put it in polar coordinates, this is what you get, and the two limits coincide in the center of this spiral. Okay, this is an example of traces of ants looking for food sources. The nest is in the middle, and what you see is basically a simulation of random processes that really represent the ants. And what you can see is that these are the searching patterns over time. It's very nice. And if you look at the diversity of the trajectories, this is what you see. And basically, you see fluctuations, and these fluctuations is the interplay that I've mentioned to you between exploitation and exploration. This is basically the exploration, and this is the exploitation. What you see is the diversity. So when you have exploration, it is inevitable that to have greater diversity, okay? Meaning that, for example, in the case of the ants, you have wandering individuals looking for the food sources. And this is the exploitation. When you have exploitation, you can expect that these wandering ants will settle down at the food source, and some other ants will come over and join them. And this will bring about order in the system. There are some other examples in which I've just played with the parameters. And what I want to show you now is how this simulation happens in real time. So I got it over here. Just a few examples. I got one with two nests somewhere. Let me find out it. Three nests. Okay, basically I'm done. I'm ready for your questions. Thank you very much. Thank you.
Surface, right? And then when he goes out from bar, he wants to go home, but he's drunk and he doesn't know the direction. And if the probability of going to any direction is the same, I mean, so
Random walk.
something like a random walk, and then
Yeah.
If you try it like infinite times, you will
Yeah,
find
yeah,
it out.
that's right. Yeah.
But if, for example, the bird drinks, it will never be able to find its nest because it's like three direction, like it's three dimensions. So I mean, it needs to go up, down, and you know.
What you say?
I don't understand why so. I mean, if the limit when the guy is drunk, approaching infinity, he's able to find his house, right? But bird is not. Why so?
You mean it cannot return to its origin?
Yeah, like not origin. Like for example, let's say bird also drinks and
Hmm.
goes to some bar, which is other tree, right? And then from this tree to this his nest, its
Ah.
nest, it can't go. I don't know why. I mean,
You mean a
the bird,
three-dimensional random
yeah,
walk?
interdimensional random walk. I think it's called random walk, right? I mean,
Yeah, it is a random walk. However, when you have in continuous spaces, it should return. There is a recurrence theorem known as recurrence theorem. It should return infinitely many times to any site, to any location in the space.
in the space or in the surface.
Well, it doesn't really matter. It can be n-dimensional, so it will always return. You see, it might take a long, very long time, a very long time. However, for a random walk, he should return to his site. Um, yeah, there are some other examples. Well, this is not really random walk, but Markov chains. It's very much related. And in that case, they have what is known as stationary distribution. This is the equilibrium, meaning that if you begin from a certain point, it will converge to some sites and it will not return back. There is the probability approaches zero that it will return to its initial condition. So I'm not sure that this is what you are, it might be the thing that you are talking about.
And so, why I'm telling this because you remember in the slides you said about like gambling. If you gamble like twice, and
Hmm.
so if like if I have really unlimited wealth and I gamble like really, I mean I don't know billions times, why is it approaching zero?
So this is because of the probability. I told you about it, the probability of winning when you do only one experiment. Now, you have to bear in mind that if the probability is exactly f, then you have your chance of winning and losing is about the same. So you basically stay on, if you take the average, you stay with your initial stake. You will not gain more and you will not lose it. However, if the probability is less than half, then this is like a convergent series and it will approach zero. And this is very much, it has to do also with random walks because one of the properties of random walks, which is one of the extensions of Brownian motion, is that when you take the expectation is the average, it would be zero, meaning that the person, the drinking person you are talking about will wander around, but if you take the average of that, it will not move from its first place. You see what I mean? Yeah, yeah. In that case, well, the integral is merely the limit of a sum. But yeah, it will not move. And this is one of the properties of random walk. However, you have some other formulations in which you have a drift. Drift, meaning that you have some term that diverge over time. And meaning that the average itself drifting. If you have average on zero, then you do all your fluctuations around this average of zero. However, if the average itself drifting, then you do all your fluctuations around this average. But it drifts over time. And this is one of the formulations of random walks. And I think that what you mentioned, and that you cannot really return to your original site, is very much has to do with Markov chains and equilibrium. You begin this is a chain, yeah? A chain meaning that it has some relation to the past. This person remembers where it was before, and it just continues from this point. So what happens in Markov chains that over time, they tend to forget their initial position and approach equilibrium. And they never really, when you get to equilibrium, you will not be able to get out of that and to return you to your original site. So it might be related to your stuff, but if you have something formulated, it will be more clear for me.
No, I was just thinking about it just now.
Yeah. And it doesn't really matter how many dimensions you have. It can be formulated even in infinite dimensions. Yeah.